All right, lesson 2-6. Today, what we're going to do is, if you look at the title of this lesson, you can see up at the top. What's the title of this lesson? What does it say? Yeah, what kind of function model validation? Just competing. Just competing. Okay, we actually covered this lesson in Unit 1. And I said, if you go back and find it on the video, I think it's lesson 113, I think. If you go back and you play it from the start, I say, hey, at the end of just about every function that we cover, we're going to have this lesson come up on repeat. Because what we're going to do today, it's the lesson and what we taught, not only scatter plots, but we looked at residuals. Do you remember residuals? Y'all remember that? Yes? No? Residuals. You remember what that was? No? Well, y'all need to start remembering the stuff we teach. This is an AP course. You need to remember stuff, not just go over it and forget it. That's what we're going to do again today. Specifically, we're now going to compare linear, quadratic, and exponential. So if you go back to lesson 113, we were comparing just linear and quadratics. That's what we did on 113. But now we're also going to compare exponential models as we go. So to begin, as I have been explaining, if you read this, we're going to come up with this lesson just about at the end of every single function we cover. So that's why I say we'll have many opportunities to work with and create models. All right. On the AP exam, then this is why I'm telling you, you can't just forget it. You're going to be expected to determine an appropriate set of data. Okay. So this is very important for you. It's not just, hey, we got to do a calculator lesson today, then let's move on. This is very important because a lot of your AP exam is going to be, are you smart enough to interpret data and figure out what type of math function it is? I think a lot of you go through math like this. I'm just going to go to math because my counselor signed me up and I'm supposed to, but math doesn't really, it's not important to me, don't need it, and you never actually internalize what any of it means, which is, by the way, a very foolish way to go through any education class. If you're going to be sitting in class, you might as well internalize it and learn what it means. What we're going to do today is we're going to make sure that when we see data, you know how to interpret and say, I know what type of function this is, so that you can make true predictions from it. Okay, this is going to help you in the real world. If you have, especially the more and more our world goes in technology, the more and more you're going to have to be able to recognize data. And data, by the way, is a mathematical quantity. It's not a science. Well, science is just applying a mathematics. It's not an English quantity. Data is a mathematical quantity. So it's going to be important for you to know this. So first, let's go over our functions. When you have a linear function, what is the most obvious thing when you look at a linear function that you observe? A straight line, which means to be a straight line, what has to be true? What about the AROC? Very good. It's constant. And so when we get data in the real world, a lot of times it's not perfectly constant. But if you look at this data, if we found our AROC, go ahead and do this. Let's do an AROC table. You will see that these values in the real world will be similar if it is linear. So for example, how much do I change from going from 1 to 2.6? 1.6. And I'm going to do the plus. Again, I always do on the y's. I don't do so on the x because the x should always be increasing from 0 to 2. How much should I increase by? 2. Okay, and then I go to the next value. How much do I increase from 2.6 to 5? 2.4. Now you can see that this isn't perfectly constant, but we can, as we go down, we'll see that our values vary vary that way. They differ by a small amount. How much do I increase by this time? 1.4 over 2. And finally, 2.3 divided by 2. Now, are these perfectly constant? No, but here's the key word over here. It has a relatively constant rate of change. The rate of change over here is always between, when you divide these by 2, it's in between. This is the smallest, 0.7. The values, the AROC is between 0.7 and which one's the largest? 2.4. And when you divide that by 2, we get 1.2. You can see how close those AROCs are. It's a relatively constant rate of change, meaning they're very, very similar values to each other. There's not much of a change. You following that? A linear has very little change in its AROC. Okay, how about quadratic? Now let's take a look at quadratic. Let's do the same task. Okay, what's happening this time? It's decreasing by 5.05, I believe. 5.05. And then we would divide by 2. Okay, now how about this time? This time I'm decreasing by 1.85. 1.85, and then you would divide that by 2. Now notice, are these numbers really close together like all the previous ones? No, you're already seeing there's a gap in this quadratic function. Okay, how about here? This time we're not decreasing. Now we are increasing by 2.1 over 2. And then finally, how much do I increase by here? 4.6. And again, this is over 2. So this time you can see the AROC, it's not constant at all. But what is happening each time on a quadratic function is that they're always increasing or they're always decreasing, because a quadratic is either concave up or concave down. In this example, are we concave up or concave down? Concave up. Because we're concave up, because this is concave up, the AROC is always increasing. It's getting bigger and bigger each time. Does that make sense? Now, you may also remember if you find a delta AROC, so go ahead and put another column over here. If we did a delta AROC column, this would have very little change. This would be relatively the same amount. So how much am I changing from here to here? I'm increasing by, it looks like, I increased by 3.2. I think this is an increase of 3.2, if I'm not mistaken, divided by 2. I think that's an increase of 3.2 over 2. Okay, how about this time? From negative 1.8 to 2.1. That's an increase of 3.95 over 2. And then finally, the increase this time would be from 2.1 to 4.6. How much of an increase is that? 2.5 over 2. So you can see that the delta AROC, these are relatively close together. You see how the delta AROC is relatively close? And that's what it means here. The delta AROC, you want to put this note, is relatively constant. What that means is it's not perfectly constant, but it's close to being constant. All right. Now, what I want you to know when you look at an exponential is that we will still find the AROC first, but we're going to see something a little bit different this time around. So let's add ourselves an AROC column. So how much do I increase by from 0.5 to 1? 0.5. 2. Okay, how about from 1.9 or 1 to 1.9? 0.9 over 2. How about from 1.9 to 4.2? 2.3. And then finally from 4.2 to 8.8. 4.6. Okay. Do you know what's happening to our delta AROC each time? I want to use the term relatively. What's happening relatively? I hear increasing, but there's a better word. These are proportional, which means when you look at these, I didn't put the pluses on them. These are being multiplied by a certain amount. Approximately how much is each number being multiplied by? No? The numbers are basically being doubled. If you look down there, they're approximately being multiplied by 2. I'll put that over here. They're approximately being doubled by 2. Approximately being doubled each time you go down. So each time they're being multiplied by 2. So when we use an exponential values, it's when the output values are roughly, here's what it says here, roughly proportional. That just means you're multiplying or dividing. So as you can see, these are getting multiplied by 2. They're being doubled roughly. Okay, that's the idea. And again, this was always increasing because this is also concave up. I'll go ahead and put that over here. This is concave up, and therefore, because it was concave up, all the AROCs are increasing. But how they're increasing is they're being doubled. Over here, they weren't being doubled, because if it were being doubled, a -5 would become a -10. That's not what was happening. Here, they were being added by a certain amount each time. So that's the whole point here. And if I wanted to put the range kind of like I did over here, this range, the range was from 1.25 is less than or equal to the delta AROC, which is less than or equal to the greatest change is this one. You divide that by 2, and we get 1.975. I know that's a crazy number there, but that means the delta AROC were always between 1.25 and 1.975. The whole point is say, the way to determine, you can look at the AROCs, you can look at the graph of the points. We're not going to have perfect values today, but we're going to look at values and make determinations from there. Okay, that was a long introduction. But on all of these, what math did I do to determine what type of model it was? AROC. We did AROC, okay? So with that introduction, let's take a look at some examples here. So we have selected values from several functions are given the tables below. Sketch the scatter plot for each table, then determine if a linear, quadratic, or exponential model is most appropriate. So let's follow the instructions. We'll go in order. Let's first plot the points and then determine which model we think is most appropriate, and then I'll prove it with the AROC. Okay, so let's plot the point 0, 11. Which two directions do I go for 0, 11? And I'm going to say y equals f of x up here. Where would I put 0, 11? Come on now, you got to know how to plot points. Up, down, left, or right? Up 11 units. Put a point. Okay, how about 2, 8.2? Right 2. Up a little bit past 8. Okay, 4, 5. Which way do I go 4? Which direction? Right. Right, and then up. Perfect. 6, 2.3. Somewhere in there. And finally, 8, -1. Here's a -1 right there. Okay, looking at this data, what type of model do you think this is? Linear. I agree. This appears to be linear to me. I'm going to try to just do a, oh my goodness, why didn't I do it? There it goes. I'm going to try to do a line of best fit through there. If you have your ID badge, just kind of put one that's kind of in the middle. This to me looks like it's linear. That right there that I added would be called the line of best fit. Line of best fit. That's what I did right there. If you're wondering what is that, that's the line of best fit. This looks to be a linear equation. It looks to be linear to me. Would y'all agree with that? Okay, so what would that mean is true about our AROC? So let's now go make our AROC column here. Let's make our AROC column. Now, what should we observe when we do our AROC column? What should happen if it's linear? They're going to be relatively constant. Here, I want to say it again. What should happen with my AROC column? Hey, I need more people speaking up. Evelyn, what should happen with my AROC? Relatively constant. Hugo, what should happen with my AROC? Relatively constant. Let's find out. When I go from 11 to 8.2, this is a little mental math day here. 11 to 8.2, how much of a change is that? -2.8. Good, Giovanni. And how much did my x's change? By 2. Okay. And then how about from 8.2 to 5? negative 3.2. And we're changing by 2, okay? How about from 5 to 2.3? And again, dividing by 2. Finally, 2.3 to negative 1. Negative 3.3, and we're dividing that by 2. Okay, when you look at those values, what can you tell me? Is there a clear pattern? Are they always increasing? Are they always decreasing? No. They're kind of going back and forth, but are they relatively constant, meaning within a certain little range of each other? Yes, they are relatively constant. So add that word underneath. These are relatively constant. Make sense? Okay, let's look at part B. Let's plot these in. Again, on the y-axis, I'm going to put y equals f of x, and we're going to plot these points. So negative 1, 2. Which two directions do I go?
Go left 1 and up 2.
Left 1, up 2. Good. Plot that point. 1.5, 5.5. 0.5, 5.5. Right there. 4, 10.5. 6.5, 5.75. 6.5, 5.75. 6.5, 5.75. I'm going to assume is somewhere in there. And 9, 2.5. 9, 2.25. I'm sorry. 9, 2.25. Okay, when you look at this model, what does that look like to you? It does look concave down. So what type of function do you think this would be? Linear, quadratic, or exponential? Quadratic. I'm going to guess with you. I think this is quadratic. Now, if you were going to come up with a line of best fit or a curve of best fit in this case, this one would be a little bit harder for me. I could try to use a tool. I don't think my tools are very good for parabolas here. Where is a parabola tool? I don't even see it. I know I have one somewhere in there. I'm not sure where it is. Okay, well, if you're going to try to draw a curve of best fit, this would be a tough one to go through. It would probably look something like this. My guess is it would come up kind of like that and do the same thing over here, kind of split them like this. That would be my guess of what the curve of best fit would look like, to try to make it look like a true parabola. So that, I'll just say a curve of best fit. Now notice this one, it's harder to go through the points. Like if you go through the points, it's going to look more like a V, an absolute value. But what should we observe on the table if we did the table? It should always be decreasing. Why decreasing? This is concave down. We should be seeing something that's decreasing as we go. So let's find that out here. Let's do our AROC column. 2.5, 2 to 5.5. How much of a change is that? 3.5. So it's changing by positive 3.5, and you would divide that by 2.5. Okay, how about from 5.5 to 10.5? Increases by 5, and this increases by 2.5. Here I did a plus. I don't ever do pluses on x's because they should always be increasing. Okay, and from 10.5 to 5.75. Negative. Okay, so good thinking on that. It's actually not quite a full 5 decrease. A 5 decrease would be to 5.5. So this is actually decreasing by 4.75. And then finally, from 5.75 to 2.25, we decrease by 2.5. Okay, now here's the problem in this one. These are these all decreasing from one to the next to the next to the next? Are they all decreasing? No, that's why these models don't look good over here, is because this actually increases, but then it's decreasing and then increasing again. That's the problem on this one. And ultimately, that's why it doesn't look that good. That's why it doesn't look that good. Is that these points here, we probably should have this one. I don't know, true data. This one would increase by 5. This one would be 3.5, and so on. Okay, so that's part of the reason that one doesn't look as good. You're supposed to always be increasing or decreasing. That's the idea of a quadratic, is the concavity. And then if you did a delta A rock, have something relatively constant. But this one's not going to look as good. So I'm going to leave it there, though. We were able to determine from the dots, we thought it was quadratic, but it's not going to be a very good equation. We could go with the calculator. Your R squared would not be very good. Let's do one more here. Part C. 110. Where would I plot 110? Right 1, up 10. Okay, good. And one more time, I'm going to do y equals f of x. 3 and 5.2. Okay. 5 and 2.4. 7 and 1.3. And then 9 and 0.7. Okay, what can you tell me this time as you look at it? It looks like exponential. So is this exponential growth or decay? Good, because it's decreasing. This is exponential decay. And so a line of best fit, I'm going to try my best just to cut through as many of those points as possible. I said line of best fit. I shouldn't say line of best fit. What should I say instead? Is that a line? I'm going to say curve of best fit there. Okay, that's our curve of best fit. So what will be true about the A rock if we examine the A rock?
That should be decreasing.
It should be decreasing because it's concave down, good, but there's something else that's going to be true. Is it going to be decreasing by the same amount like quadratic's supposed to be?
No.
So a true graph that had good points, if it was concave down, not only would they be decreasing, the A rocks would be changing by decreasing. What's happening though on a exponential, what I'm looking for is that it should be this one decreasing at a proportional rate, meaning it's being multiplied or divided. Okay, so let's see it here. How much do I change going from 10 to 5.2? Negative 4.8, and my x's are changing by 2's this time. Okay, now from 5.2 to 2.4, I decrease by negative 2.8. Mental math isn't always that easy. Okay, how about here? That's right. Giovanni, I'm thankful that you always are trying. All right. And then here. Negative 0.6. All right. So now observe the values. Do they look like they're changing by a constant amount? Are they changing by a constant amount? No. That's what quadratic would be, where these are changing at a constant amount. These, what happens to the values? Approximately. What's happening to these values? It looks like they're being divided by 2, if you ask me. Does it look like it's being divided by 2? These look like it's a proportional change. That's a proportional change. And so what does that mean? I would say the y's are being divided by 2, or delta y, I should say. The change in the y's, delta y, is being divided by 2. That's what it looks like to me, is that the y's are being divided by 2. Make sense to you? What you're looking for? So if it's a linear, what you'll see is that the A rock is relatively constant. What you'll see if it's quadratic is that the A rock is changing by a constant amount. Although this one was just bad data. I just need to fix it for the future. On a exponential, the A rock is changing, but it's changing by proportional amount, meaning not a constant amount. It's being either multiplied or divided by a certain amount. And that's what was happening here. Okay, so I got one more. Sorry, I thought I was only doing 3. I got one more to do. Let's do one more. Did I write exponential on this one? Yes, I did. Okay. Let's do the last one. Let's figure out what this is. So again, I'm going to title my y-axis y equals f of x. It's very important you know that f of x represents your y values always. So I'm going to do that all year just so that you don't even think twice about that. X is left 2. Y says go up 2. Or f of x says go up 2. 1 right, 3 up. 4 right, 4.5 up. 7 right, 6.7 up. 6.7, wait, 7 right, 6.75, sorry. Got switched around. Okay, and then finally 10 to the right. Ooh, I don't have space for that. And then 10.25. I'm gonna have to put one on there right here. There's 10. And there we go. Okay, as you look at this one, what does it look like to you? This one's a little bit trickier. I would say exponential as well. Exponential growth or decay?
Yeah.
I would agree. It looks like exponential growth to me. So what does that mean about my A-rock when we find it? What do we expect to see in the A-rock? Changing by, or relatively constant, or the A-rock's changing by a relatively same amount, or that the A-rock is being multiplied by a relatively constant amount? Multiplied. All right, let's find this out here. Desiree, how much am I changing by going from 2 to 3? 1. And my x's are changing by 3 here. Okay, how about 3 to 4.5? By 1.5? Now, here's what I'm trying to say. If this was quadratic, if it's linear, you're expecting to see the same amount every time, or relatively the same amount. If it's quadratic, you see how this increased by 0.5? You're expecting this to increase by about 0.5. You're expecting it to change by the same amount every time. But how much does this change by? 2.25, which you're at this stage, if it was only here, you could be going, that might be quadratic. But this one will really give it away because you're like, well, it increased by 0.5, now 0.75. That's okay, but this one will really give it away, whether it's exponential or quadratic. From 6.75 to 10.25. 3 point how much? 5. Okay, so now we should really be able to tell. This increased by 0.5, by 0.75, by 1.25. Does that seem like it's increasing by adding the same amount each time to that? Does a delta rock act like it's the same every time? No. That's why I would say this is a proportional change. If this is a proportional change, that means you're multiplying or dividing by some amount. That's what I think is happening each time, is I think these values are getting multiplied by approximately 0.5. I'm not sure. Let's just check it out. I'm going to go to the calculator just to show you. I want you to see this. So I'm going to slide it where you can see the table here. I think what's happening are the y values are getting multiplied by about 1.5. And so I'm going to just try this. So if I took 2 and I multiplied that by 1.5, what do we get? 3. Is that what the next value was? And if I take 3 and I multiply that by 1.5, what do I get? 4.5. Okay, if I take 4.5 and I multiply that by 1.5, what do I get? Do you see how the table is being built? This is, in fact, this is proportional change. All of these are getting multiplied by 1.5. And I saw it from here before seeing it over there. That was a little bit harder, but those I knew was multiplying by 1.5. Anyways, that would be exponential growth. Okay? Questions over that? How to determine what you're looking for. All right. So now let's review what we talked about residuals. At the start of the lesson, I talked about this and y'all were pretty silent. So when we create a model, our model predicts values. I'm going to say this again. When we create a model, what does our model actually do? It predicts values. Does that mean our predictions are always accurate? No. A residual is measuring how accurate our model is. Our residual will measure how accurate it is. Okay, so what does a residual measure? how accurate it is. And here's the formula. You need to know the formula. It's that you take your actual value and you subtract it by the predicted. It's always actual minus predicted. The closer those numbers are to 0, the better it is. Let me just think about that. If you wanted a good model, should your model predict good value or close values or way off values from what the true value is? Close. So if the values are close, an actual minus predicted should give you what number if they were perfectly accurate? If let's say the actual is supposed to be a 10, your model's predicting a 10, what's 10 minus 10? 0. You want numbers closer and closer to 0. Does that make sense? The error right here is when you take your actual minus the predicted and you ignore if it's negative or positive. We just say, hey, if it's 0.5 off, we don't care if it's too high, too low. If it's 0.5 off, we say the error is 0.5. Does that make sense? When you do the math, sometimes you'll have positive numbers, sometimes you'll have negative numbers, but the error itself is the actual minus the predicted, and then you make the value positive. If it is already positive, it stays positive. If it was negative, it makes it positive, okay? All right, are you understanding? Give me a thumbs up if you're following what I'm saying. What's a residual do? It tells you how accurate it is. And what is the error? It shows you how much it's off. Yep, it shows you how much it's off. It ignores if it's negative or positive. You don't care when you find error. If it's negative or positive, you don't care about that. We might just say it's an underestimate or overestimate, but we don't care about the negative part. Okay. Example 2, the weight of newborn babies can be modeled by a linear function. They told us what type of function it is. What type of function is it? Linear. I would always box that up when you come across it. For the first 4 months after birth, selected values of the weight in kilograms of a particular newborn baby are given in the table to the right, where T represents the number of months since birth. Use the regression capabilities on your calculator to find a linear model in the form y equals a plus bx for the weight in kilograms of this particular baby x months after birth. All right, let's go to our calculator and do this. So we're going to type in that data. Where'd my calculator go? There it is. I'm going to go home screen, new document. I'd suggest you do the same. Home screen, new document. Let's clear it all out. Where do we go to find a regression? Listen, spreadsheets. Good. I'm going to title my columns just like they did. I'm going to title it T, and I'm going to title it W. And after you type in your data. For real? You're lying. You're lying to me. We need to get to a regression. What buttons do we press to get to the regressions? Menu 4, 1. Now, this time, there are 2 linears. Which linear did they give us? Did they give us mx plus b, or did they give us a plus bx? So choose that one. A plus bx. What do we put for x list? What was our independent variable? T. Whoops. T. And we titled our y list W. Make note of where it's going to save it to. It's always, if you clear your calculator, it should save it to F1. If you did not clear your calculator, it could be somewhere else. Make note where they save it. All right, press OK. Here's our equation. Is this a perfect regression? No. How do you know it's not perfect? The R squared is not 1. The R squared is not 1. I think if I remember right. No, I need to look that up. And I don't think it means residual. I forget what they use the R for. Okay. Hey, back up here. This is going to create our equation. I'm going to highlight these 3 things right here. The reason I'm doing this is this shows me what my equation is. This shows me my variables. Okay. So I'm going to copy that over. All right. I know that's really small. You probably can't see it right now. But this is my A, that's my B right there. These are my values. So my equation should look like, it says use y equals. And honestly, we should use W. Instead of y, what is y represented by?
W.
So I'm going to say W of t equals A is 3.34 plus B, which is 0.8. And then instead of an X, I'm going to use a T. That would be my model. That's my model W. Now, part B, use the model found in part A to predict the weight in kilograms of this baby 2.5 months after birth. Okay, what is 2.5 months? Is that a T or a W? That is a T. This is when T equals 2.5. So now what we're going to do is we're going to go to the calculator and type in not W of 2.5. What are we going to type in instead? F1 of 2.5. So hit Control. What button do you press to get a new page? Control Doc. Add a calculator. F1 of 2.5. When you hit enter, you getting 5.34?
Yep.
Perfect. So 5.34 is what we got here. Now, this is weight in kilograms, so I want to say 5.34 kilograms. Make sure you put the unit as well when you write your answer. Make sure you put the unit. All right, now the actual weight of the baby, 2.5 months after birth, was 5.5 kilograms. Okay, so here's the question. Is this model perfect if the actual was 5.5? No. So what is the residual for this weight? So here's how you find the residual. The residual is the formula. I gave it to you already. What was the formula for the residual? And I'm going to, that's right. It's the actual. Yeah, what's the actual weight? 5.5. This right here is the actual. So it's going to be 5.5 minus the predicted. So in our problem, what is our predicted weight? 5.34, what we just found on part B. So if we subtract those, we get the residual. To make sure I don't make a mistake, it's 5.5 minus 5.34. I'm getting 0.16. Now, this, if it's a residual, you would keep the Y units. 5.5 was what type of units? Kilograms minus 5.34 kilograms. So how many? My 0.16 would be in kilograms. That's the residual right there. That's the residual, okay? Now, this has multiple little questions right about this value. If that's our residual, what is the error? So the error, you just take the positive of this value. Well, it's already positive, so what do I do to that? You take the absolute value, I should say. The error is equal to the absolute value of 0.16. What do you do when you take the absolute value of something? It either stays positive or you make it positive. So in this case, it stays as 0.16. And I think the units would stay. That's the error. The error stays the same. Next question. Did our model overestimate or underestimate? Here's what you need to think through. Which one's the model? Is the model 5.5 or was the model 5.34? This was the model. Did the model overestimate or underestimate? Is this one bigger or smaller than the 5.5? This one is smaller, so we underestimated. Our model underestimated the weight. I'm just going to type that in. Our model underestimated the weight. Our model underestimated the baby's weight by 0.16 kilograms. Underestimate is the word here. Now, the reason it was an underestimate is because the residual was a positive. If it's a positive number, just mathematically, if you think about it, to get a positive number, that means the actual is bigger than the predicted. If the actual is bigger than the predicted was an underestimate. We estimated too small. So that's why it's an underestimate. If your residual is negative, then you overestimated. That would mean the predicted was bigger than the actual mathematically. Go ahead. Okay, so this is an underestimate. Now, we've gone through a whole bunch of problems. I've got two for you to try. I want you to try number 1, followed by number 4 on the back of the packet, okay? DOL number 1. One thing I've forgotten to show you is how to find the residuals on the calculator. So from our calculator, press Control Dot to get a new page. Once you get a new page, I want you to choose Data and Statistics. Now, what you will always do, always, no matter where we are in the school year, no matter what you're finding, is you'll always put whatever your x variable is for the x-axis. That will never change. Which variable represented x in our problem? Give you slide that over. Which variable was our x? T. Now, depending on what we're doing throughout the school year, you might change your y-axis. On this problem, we want to look at the residuals. That's the thing I forgot to show you, the residuals, meaning the error of the problem. So on this problem, you would look for residuals. Do you see residuals? There's twice. I don't know if there's any difference. I'm going to try it real quick. I'm going to do the first one, and then I'm going to click the second one. Let's see if there's any difference. No, there's no difference. So just check the one that says dot resid. Are you getting that? Okay, just to make sure everyone's clear, this line right here, that is the estimate. What does this line refer to right here at 0? That's the estimate. The dots are the actual values. What are the dots? Actual values. What's the line? Estimate. Okay, this point right here at 0. Is this point the estimate or the actual? Actual. The estimate's here. This value here would be an overestimate. I'm going to say it again. It's an overestimate. Why? Because my estimate is over, meaning above the actual. Make sense? What about the x value at 1? Are we an overestimate or underestimate? It's an underestimate because the estimate is under the point. Everybody follow? What about at the t value of 2? I said x a minute ago. I should have said t. The t value of 2. Is our model an overestimate or underestimate? It's under because it's under the actual. What about at t equals 3? It's under. And then t equals 4? Over. That's how you do that. So you add a data and statistics, put your x-axis, then choose residual. That's how you see it to find your error. The error, by the way, I didn't say this. The error is the y value. So here, what's my error on this problem? 0.06. Here, the error, even though it says negative, you would say your error is 0.14. It's a overestimate by 0.14. Does that make sense? The residual itself is negative, but the error, you just always say the positive of it. What's the error on this point right here? 0.16. What's the error here? 0.06, and then here, 0.14. You wouldn't say the negative, you would say the error is 0.14. You always list it as positive. All right, with that, go back to those DOLs I gave you. All right, as I pick back up, let's review. You can tell the appropriateness of a model based off the residual. Do you remember? What tells you when you look at a residual if it's a good model or a bad model?
No pattern, right?
No pattern. No pattern, good. A pattern on residual is bad. No pattern's good. A pattern is bad. Okay? This one. Pattern, no pattern.
No pattern.
Does that look like a pattern to you?
No.
It doesn't look like a pattern to me. Since there's no pattern, what does that mean? It's a good model. Now, let's see here. An exponential regression was used. So it doesn't look like a residual. It doesn't look like an exponential. A residual should not. A residual is showing you the error in the model. This is a good model. Exponential, I should put that on here. Exponential would be a good model. Exponential is a good model. Now, if you wanted to see the model, instead of choosing residual in your calculator, this is when you would just do your y variable. If you do your y variable, you'd get a scatter plot, and that would show you it looks exponential. The residual doesn't show you the model. What it does is it tells you the error, and you can tell whether it's accurate or not. That is a good model. Okay? It looks like all the values are within 2. Nothing is outside of 2. The error, the greatest error you ever have, it looks like is this point, it's less than 2. So this is a very accurate model. It predicts pretty good values. Okay? So you could look at this problem here. Just quick glance. Which model is the best? The linear at the top right, quadratic in the middle right, or exponential at the bottom right? Exponential. Why is exponential the best? No pattern. Okay, I want you to try number 2 and number 5 on the back of the packet now. Try number 2 and 5 on the back of the packet. Example 4. Mr. Passwater hopes to make it into the Guinness Book of World Records by painting the world's biggest mural on the sides of several downtown buildings. His mural will consist of many painted circles of various sizes, where each circle is painted a different color. He wants to create a model to determine how much paint is needed in quarts for a circle of radius r. Should Mr. Passwater use a linear, quadratic, or exponential model in this situation? Explain your reasoning. Okay, so let's think about this. You're trying to paint, and it gives me one thing about what type of shapes is he painting? All right, so you're going to be painting circles, and you're trying to decide how much paint is needed to paint these different circles. So my question for you is, what type of model would this be? Because it doesn't say anything to us. What type of model do you think you would use here? Would this be a linear? Would this be a quadratic or an exponential when you go to buy paint? Why quadratic?
Is it not like painted in different colors? So like, is it that way?
It's not because he's painting different colors. Y'all are correct when you say quadratic. It is going to be quadratic. Quadratic is the correct answer. But why is it quadratic?
This is important.
Okay, more paint, the bigger the circle gets. There's a different reason. Mathematical reason. It does say radius, but that doesn't necessarily tell you your answer. Why would this be quadratic? Let me ask you this. What principle did I just use doing this? Is this perimeter? Is this area? Is this volume? What did I just do here? When I painted those, what type of that is that? Is that perimeter, area, volume? This is area. Your paint is going to be following area. You're painting an area. Let's say it like that. Painting an area. Okay, different question. What's the formula, the area formula for a circle? I'll put parentheses radius. Do you remember? Pi r squared. Pi r squared. That's your formula for radius, where the radius can change, and depending on what the radius is, you can find your area. That's the formula right there. Now, when you look at this, what is my variable? What is my input variable? Radius. And what's happening to the radius? It's being squared. What type of function means you take your variable and square it? Non-exponential. That's where your variable is the exponent. It's quadratic. That is quadratic. Okay, that is a quadratic equation. Okay, now part B. After creating his model, Mr. Passwater uses it to purchase different special paint colors to use on his mural. In this situation, do you think it's more appropriate for the model to underestimate or overestimate the actual amount of paint needed? Give a reason. What do you think is more valuable, to underestimate the paint needed or overestimate? Very good. Over. Why is it more appropriate to overestimate? I like what Miriam said. We need to overestimate I should say he should overestimate because, as Miriam said, it is better to have extra paint than to not have enough to finish the mural. That would just be embarrassing if you were painting on the side of a building downtown and you ran out of paint, you weren't able to finish your painting. That would just be embarrassing. So yeah, he should overestimate the amount of paint. Should overestimate how much paint to buy. It's better to have extra paint than not have enough to finish the mural. Okay, with that, I know this says here DOL 3. There are 2 DOLs we have not done in the back of the packet. This one says try number 3 in the back of the packet. But after, we're going to go immediately into DOL number 6. So you might as well do both of those. Do number 3 and do number 6. Okay, do number 3 and number 6. And then you can submit your answers online to make sure you got them correctly if you desire to do so.